I think it's a like
Hey, I mean, yeah, but I'm an honorary. Adrian, we're not in the cup, but like, yeah, he's head taste, but I've been to every meeting. Head taste too. Exactly. Yeah. That's I have to make sure. That's an important job.
Hi everyone. Before I get into the new stuff, do you guys have any questions about optimization or 6.1 or anything else that's kind of like still dangling that we haven't come back and addressed, Adrian?
Maybe if we could do like example from the optimization set too. I feel like that would be helpful.
Yeah, which one are you looking at?
Probably the last one. It was like the
lifeguard. That's the trickiest one, right? It should have.
Yeah, it's the lifeguard question felt hard.
Lifeguard?
Life.
Is that two? Is that two or one?
Yeah.
Is the test grade? God, I hope not. No.
Yeah, actually.
Don't read them till next week.
All right, so our lifeguard problem reads as follows. A lifeguard is stationed 100 meters inland from a straight shoreline. A swimmer is in distress 200 meters down the beach from the point on the shoreline closest to the lifeguard and 50 meters offshore. The lifeguard can run at a speed of 6 meters per second on sand and swim at a speed of 2 meters per second in water. The lifeguard runs along the sand, enters the water at some point along the shoreline, and then swims directly to the swimmer. How far should the lifeguard run along the shoreline before entering the water in order to reach the swimmer as quickly as possible? So I'd want to start by drawing myself a diagram of what's going on. So let's say like there's my shoreline. There's my lifeguard. And there's my swimmer. Everybody feel okay? We're told that the distance from the lifeguard to the shoreline is 100 meters. We're told the distance of the swimmer down the shoreline is 200 meters. And then he is 50 meters out to sea somewhere, right? Yes. For part of it, yes. Or kind of the distance formula, whatever you want to think about it as. Okay. So what we need to be able to figure out is like some point here on the beach, because we're going to do one of these. Right, we're going to run along the sand till we get to the shoreline, then get in the water and do some swimming. And we want to figure out like where we should be entering the water so that we can get to the swimmer as quickly as possible. Does everybody feel okay? Now, if the running speed and swimming speed are the same, well, that's easy. It's just like a straight line, right? But notice that we run a lot faster than we swim, which is the case for most people. Right? You watch the Olympics and people are basically walking along the pool deck as the guys are swimming. You know, it's hard to swim very fast. Okay, so I'm gonna calculate, I'm gonna create an expression for my distances. So I'm gonna have some running distance and some swimming distance, right? So I'm gonna say that this is x. So this other piece over here must be 200 minus x, right? That spot where I'm gonna be entering the water. So my running distance is gonna be equal to the square root of x squared plus y squared, right? So like a Pythagorean theorem. And my swimming distance then is gonna be like x squared plus y squared, or square root of, I should say. Everybody okay with kind of the picture I've drawn and the setups I've made here? Now, what did the question actually ask us to minimize?
Swimming time.
The time that it takes to get to the person. So somehow I have to create an expression here in terms of time, right? So I have distances. I want to know about time, and the other thing I'm given in the problem is a rate. Remember that distance is equal to rate times time, right? That's like a middle school science equation. So my running distance is going to equal 6 times the amount of time I run, or that my time spent running is the running distance divided by 6. And then my swimming distance is going to be 2 times the amount of time I spend swimming, or my time swimming is the distance swimming divided by 2. Everybody, so far so good. Now, what is my total time going to be then?
TR plus TR.
Good. Now, I want to write TR plus TS in terms of a single variable. That single variable is going to be X, because I've been able to write my running distance and swimming distance both in terms of X, which is that point of entry into the water, basically. So this is going to be a function of X, where I have square root x squared plus 100 squared all over 6 plus square root 200 minus x squared plus 50 squared all over 2.
This is like where I got, and I didn't really know where to go.
Okay? Brooks.
It's probably an obvious question, but where does the 6 and the 2 come from for?
That was the given to us in the problem, was the running speed and swimming speeds.
Okay.
Okay. So before I continue, now that I've written a function for the quantity I want to maximize or minimize in terms of a single variable, I want to look at the domain of this function. Okay? What is the smallest and largest values that I could have for x? Go back and look at the picture.
0.
If x equals 0, it would mean I take like that path, right? What's the biggest value for x?
200.
200, right? Where I take that path. Are those both valid paths?
Yeah.
Okay, so should this interval be open or closed?
Close.
Closed. Everybody good? Okay. since I have a closed interval when I'm checking my maxes and mins, what else am I gonna have to remember to check? Endpoints. Okay? So far, so good? I've written my function. It's in terms of a single variable. I've identified the domain. Now it's time to find my critical points. To do that, I'm going to take the derivative of t with respect to x. How do I take the derivative of this first piece?
Make it into 1/2 times all that, and then times 6 to the power -1.
I won't have to worry about the 6 because it's a constant. But I would need to use a chain rule, right? So I have the 1/6. And then the derivative of the outside is that, right? The inside stay the same times the derivative of the inside. Does everybody feel okay there? Now you could have FOILed that out and done that also, but you don't have to. Okay? How about here? What do I need to differentiate that piece?
Same rule.
Actually, 2 chain rules. Because there's the composition for the square root and the composition for the quantity squared, right? Now, could you FOIL out that quantity squared to eliminate a chain rule? You could. I'm not going to bother with it, but you could. Ready so far, so good? Okay. So I have the 1/2 from the over 2. I'm going to have 1/2 quantity, 200 minus x squared plus 50 squared times the derivative of this inside stuff. So the derivative of 50 squared just goes away.
Would it be to the -1/2 or no?
Oh, yes, thank you. And I have the derivative of that piece. And then I need the derivative of that piece. Brackets where I have. Is everybody okay?
So in that last part I just did, what was the first chain rule that you took? Was it the square root or the 200 minus x squared?
So from the outside in.
Okay.
So the square root, and then the squared, and then the 200 minus x. So now that I have this, I can do this, right? Am I actually going to try to solve this thing algebraically?
No.
Not a chance. What am I going to do?
Plug it as 0?
I'm going to type into my calculator, I'm going to graph and find the 0 graphically. Is that okay with you guys? Do I need to show doing that again, or do you just take my word for writing down the number?
Big word.
Okay, that's fine. I just wanted to know where we're at. It's something we've done before. I didn't remember, you know. There's that. Where doesn't this Well, where will this not exist?
Anywhere past 200.
Okay, well, that's outside of the domain anyway, so we don't have to worry about that. But yes, since it's not part of the domain of the function, it doesn't matter if the derivative doesn't exist there, because we knew it wouldn't if it's outside of the domain. What about at exactly 200? Are we gonna run into a problem there? Oh, I don't think so. That'll be okay. Because we still have this other guy. I just was worried about the negative exponent, worrying about a zero denominator, but I don't think that can happen since we have two positive things added together. Hey,
Wait, how do you know something would come out to be does not exist? Like, what do you look for?
so I'm looking at if there's any values for x that make this undefined that are still in the domain.
Okay.
So Brooks correctly identified that, like, hey, if it's bigger than 200, we might have a problem, but we don't have to worry about any values bigger than 200 because it's not in the domain anyway.
Okay.
And then I was like, we did pick up a negative exponent, so I have to worry about zero denominators now that I didn't have to worry about in the previous one.
Okay.
So my quick check was, can I get a zero in here? And I can't because I have something positive plus something positive in both spots. So I can't get a zero denominator either. So I'm quite sure this is none. Brooks.
I'm just making sure when y is 0, x is 184. That's what that's saying?
Yes.
Okay.
Okay. So my last piece now, this is a potential minimum, right? Or would correspond, this is a distance, we still have to convert this into a time, but this is a potential location of a minimum, but it's not the only one, right? What else do I still need? The endpoints. So I have three things to check now. So I'm going back to that original total function, total time function. So what is the minimum amount of time we need? So the minimum value there was 61.16, and that happens when we enter the water, 184.67 meters down the shoreline. What's up?
I was just wondering how many meters.
184.67 down the shoreline. How many of you guys have, dogs? You have dogs? Does a dog like to play fetch?
Yeah.
You ever play fetch with your dog by the water? Where you start in the water and throw the ball into the water and the dog goes and gets it? You know what the dog does instinctively? Finds that optimal entry point. Like when they've, believe it or not, biologists have looked at this, and the animal's built-in heuristic, hardwired into their brain, does an excellent job of choosing just about the optimal entry point for this kind of situation, which is wild to think about. That nature's actually really good at finding these, or approximating these minimums, or minimum or maximum, the best or worst way of doing something. They've tracked honeybees going to flowers, collecting pollen from flowers, and they find that the honeybee almost always takes just about the shortest path from flower to flower to flower and return to the hive to drop off the pollen or whatever. It's wild that Mother Nature is also kind of somehow good at calculus too, as an aside. Adrian, that was a mouthful, or a massive problem, right? You feel better about what we're doing?
Yeah, I think so.
And again, like, this was, like getting to here, I think is the hardest part. Right after this, it's just domain, differentiate, set equal to 0. Like the setup, I think, is massively the hardest piece in like drawing a picture and understanding like, how am I gonna get an equation for time out of this? Was tough. But this should have felt rather authentic, like a real problem that has like, I understand why we would care about a solution to this. This feels authentically like something that, somebody would care about. And like, I can't do this using like, geometry or algebra or something else, just like required calculus to do this in a way that like, the optimal shape to enclose an area is a square, kind of things. Like, well, I kind of expected that. This should feel authentic in a way that maybe those other problems didn't. Everybody okay? While we were getting ready there, I passed out the third set of optimization problems. These are not decidedly different than the set 2, other than they're non-numeric. So instead of having numbers, you're getting just like constants. So your answer is going to be an expression, which is like the final layer of, I think, the hardest level of difficulty for these kind of things, like, where you're going to have an expression with like, 2r or something is going to be your answer instead of like an actual number. Okay? Today, I want to talk about, or start talking about, volume, calculating volume. This will probably be a 3-lesson topic. There's kind of 4 techniques that we're going to study. I'm going to do 2 of them in this lesson. We'll do 2 of them in another lesson. We'll probably have like a consolidation day where we just kind of practice how do I select the proper method for the situation. Or I shouldn't say the proper, maybe the optimal. Many of them can be used in multiple situations. Just a question of like, how ugly do you want this to get? Okay. So the idea here, let's start really basically with, stuff that we would have done in like our geometry class and talk about the volume of a right figure, right? So when I say right, what do I mean? That it's perpendicular to the ground, yes. So whether we call it a cylinder because it's like the canonical classic shaped cylinder that we want, or it's a box, or it's some other weird horseshoe base. In any of these situations, the volume for the cylinder is just going to be the area of the base times the height. If the area of the top is the same as the area of the bottom, and it's perpendicular to the ground, the volume is just area of base times height. Very straightforward. Everybody's okay there? But what are we going to do if I have like some cuckoo crazy irregularly shaped object where at each cross section the area of that cross section is different along its height? Oh no, right? Well, if I think about it, could I just take like a little sliver of cross section and calculate the area and then multiply it by that little tiny height for the sliver and then add up all of those and then get a volume? Right? What does that sound like I'm starting to do? An integral, right? Right. That sounds exactly like a Riemann sum or integral, and that's exactly what we're going to be doing. That's the exact idea. Is we're going to be like taking little tiny slices, calculating the volume of that little slice, and then adding up all the slices to get a total volume. Everybody okay? All right. So this figure here, this example figure, this cross-sectional slice, this A of x is called our cross-sectional area. And we've observed that as we change our slice, as we go from A to B, the cross-sectional area is going to be different because it's smaller down here, it's bigger in the middle, and then smaller again at the end. At every slice, it's a different area, which means that that cross-sectional area is kind of like a variable. We're going to have to represent it with like an expression in terms of x. And to calculate the volume of this figure, I can just take, infinitely many of these cross-sectional slices, find the volume of each slice, and add them all up to get a total area for the figure, which is exactly where we land here. This is called the disk method, because essentially these cross-sections are end up being circle-shaped in most figures, so they look like a disk, like a coin. Okay. So let's look at some examples here. So in the disk method, this area that we're using is just going to be the area of a circle, pi r squared, where the r is going to be like a function of x or something. All right, so here we're asked to show that the volume of a sphere of radius r is equal to 4/3 pi r cubed. Okay, so if I think about this in 2 dimensions, if I have a circle of radius r, and I rotate that around, let's not do that yet. Let's not do that yet. Let's just think about my cross section here, right? Go away. Is it really not going to go away? Oh, we're just not responding. Swell. I don't know why.
I just question about what we're doing. So if it's irregularly shaped, but on both sides, like the last example, it was irregularly shaped on both sides. Do you have to take the integral from slices this way and from the other way?
No.
Okay.
No, you should be good going from just horizontally or vertically. All right, why is this not working here?
X is red.
Yeah,
So it's stuck as recording.
I don't need you to report anything.
Can I fill in water well?
Yeah.
During this thing?
All right, let's try this again. Okay, so we're going to imagine we're slicing perpendicular to the x-axis. Everybody agree with that? Which means that when we write our integral I'm gonna need to write this as a function of x. Everybody's okay with that? So for example, this point here is going to be okay, so we have like some xy, right?
Yeah.
And we know that r is going to be equal to that, right? Well, let's just say this. That's probably easier, right? So y is the radius for this circle that I'm writing, correct? So I want to rewrite this as a equation in terms of y, or I'm sorry, where it's y equals. Right, okay, there. I've subtracted x squared from both sides and taken the square root. Why did I drop the plus or minus? If this is a radius of a circle, it should have positive length. That's good. Okay. So my cross-sectional area then is going to be pi, and then my radius here is y, right? And the squared will cancel the square root. Feel good? So our volume then is going to be the integral, where we're starting here, and we're going to slice all the way until we get to here. Everybody agree?
How big are the slices gonna be?
Infinitely small, infinitely thin. That's what we're doing when we do an integral. Everybody's okay with that? And we have pi r squared minus x squared dx. That's our formula, right? So the area of the circle times the dx, that's like the width of the slice, like an infinitely thin slice, or infinitely thin width. Okay? Now I can integrate this as I would normally. So I'm going to pull the pi out front. What is the antiderivative of r squared in terms of x?
R cubed divided by 2.
Nope. Nope. What? R squared x. Why? R squared is a constant
Ooh.
because we're different or integrating with respect to x. So r squared is not a variable. R squared is a constant. The derivative of x, or the antiderivative of x squared is
X cubed divided by 2.
x cubed over 3. Everybody feel okay? And now we will finish our, yes,
Sorry.
that's okay.
Why do you multiply the x if it's not like r squared x?
Right, the antiderivative of a constant is just x times the constant. R squared is a constant. Is that okay?
Yeah.
Okay. Everybody okay with what I did? Okay, so let's see what I got here. So r cubed minus r cubed over 3 is 2r cubed over 3. Then I have minus a negative, so like that's going to make it a plus. And minus a negative, that's going to make it a plus. So I have r cubed plus a negative r cubed over 3. It's another r cubed over 3. Or 2r cubed over 3, excuse me. Is everybody okay? When I add those together, I have 4r, or I should say 4 pi, let's write it, 4/3 pi r cubed. That's our volume equation for a sphere. Meredith?
How did you, the A and B are negative?
Okay. So if I go back and I look at the picture, we're gonna, to calculate our volume, we're gonna start our slicing at the left end, and we're gonna cut slices all the way until I get to the far right end. So the x value I started slicing at was negative r, and the x value I finished slicing at was positive r.
So will it, like if we're doing it from a graph, will it give us like the negative r?
Sometimes you'll have to find it.
Okay.
Let's continue going forward, because this is like, we already knew the answer, right? This is a regular shaped figure. Let's look at a example. So let's say we want to find the volume of the solid obtained by rotating about the x-axis. The region under the curve, y equals square root x from 0 to 1. So this is what you should imagine in your head. If we take this figure and we rotate it around, it's going to create like a dome kind of shape tilted on its side. Is everybody okay with that? So again, we're going to start slicing at 0 and finish slicing at 1. So I know I have that much, right? We've drawn in one of these cross sections. That's like the radius of that cross-sectional disk. If this point here is x comma y, the radius is y, is the y coordinate, right? Everybody see that?
Yeah.
On this curve, y equals square root of x, what is the y coordinate equal to in terms of x? Square root of x, right? Oh my God, stop already. So the cross-sectional area is pi r squared dx. Is everybody okay with what I've done here? I'm trying to go super slow and be super careful.
The pi
Is that-
comes, the pi comes from the thing before.
Because the shape of the cross-section is a circle. Is that okay? Anytime you're like rotating about an axis, you can have like a circular kind of thing going on. So those can cancel, the squared can cancel the square root. What's the antiderivative of pi, or of, sorry, just x? That guy, right? So our volume is pi over 2. So far, so good? Eventually, I'm gonna stop giving you the three-dimensional shape, and you're gonna have to imagine this on your own. Those of you that have been doing CAD, this should come a little bit more naturally to you as you're building these three-dimensional figures in the program also, but this is one where you just gotta kind of close your eyes and imagine. All right, here it says, find the volume of the solid obtained by rotating the region bounded by y equals x cubed, y equals 8, and x equals 0, about the y-axis. So again, I've given us the graph, right? I've gone ahead and extrapolated that into a three-dimensional shape. Kind of looks like the top of a wine glass or something, like a champagne flute, right? Notice here, which way are we going to be naturally slicing? Vertically, right? So this time, instead of integrating with respect to x, we would want to be integrating with respect to y. And we're going to be integrating along the y-coordinate 0 to 8. Is everybody okay there? Now notice here, this is the point xy. And since this is there's that, right? Now, our radius here is an x-coordinate. So I'm going to need to rewrite this with x in terms of y. So if I have y equals x cubed, I can take the cube root of both sides and say x is equal to the cube root of y. Is everybody okay there? So this is my radius. So again, my shape is a circle, so it's pi radius squared. So far, so good. Okay. Let's simplify that expression a little bit. I'll pull the pi out, I guess, as long as we're simplifying things. What's the antiderivative of y to the 2/3?
5/3 divided by, 3 on top, 5 on bottom.
Everybody okay there? Okay. 3 on the bottom is a cube root, right? Cube root of 8 is 2. 2 to the 5th is 32. Times 3 is 96 over 5, and the other piece is just 0. Is everybody okay there?
Is 0 to any number?
Any power?
0
So 0 to any non-zero power is 0. 0 to the 0 is indeterminate. That's one of those indeterminate forms that we talked about in first semester.
Is a number to 0 1?
A non-zero to the 0 is 1.
Okay.
Yes. All right. So let's say we have the region R enclosed by the curves y equals x, that's the straight line, and y equals x squared. And then we're going to rotate that along the x-axis. Now imagine if I rotate this along the x-axis, I'm going to have like a hole in the middle, right, of this figure. There's going to be an empty spot because of all this empty area here between the figure and the x-axis. It's gonna be like a, kind of like a funnel, but it's closed at the bottom, right? And it's not the same thickness all the way down, because why would it be, right? Is everybody okay with that idea? You're picturing, I mean, I give you the picture to imagine, but you have to be able to picture this in your head and be able to detect like when there's an opening and when there's not. The word we use here would be like concave, right? This is a concave three-dimensional figure because there's like an indent or a hole or something in it. These other ones that we've looked at would be convex. Like there's no opening, there's no hole, there's no indent. Everybody's okay? We use those terms in geometry, right? Convex and concave. Okay. So here we have, when we cut our cross section is going to look like a donut, right? So our cross section is going to have two areas. We're going to have the area of the outer circle minus the area of the inner circle. Yes?
Why do you have an outer circle and an inner circle instead of just one area with a cone?
Because it's not a cone, because there's this, we have this open area here. So when I rotate it around the x-axis, I'm going to have like this stuff in the middle is going to be open. So like if I were to try to draw this in like me trying to draw it in 3 dimensions, it kind of look like this, where like if there's a hole through the middle, but it doesn't go all the way, like comes to a point. It's like a funnel with like the inside filled in, but unlike a funnel where it's like the same thickness all the way down, this one, it bulges in the middle and it's like skinny at the top, and you kind of see it now in the 3 dimensions. Like it's one of these where the ability to kind of close your eyes and picture what this thing is looking like in 3 dimensions is really useful. It's not a skill you have naturally, but it's one that like take some time and think about it and build that skill, because it really helps the intuition of like what you're doing for a setup. Lucas.
So we would get the first picture, just not the second two?
You may not even, depending on the context, they may just give you the words. Like that's eventually where this would be going. I know, right? I'm trying to keep the training wheels on here at the beginning, and we're going to give you pictures to go along with things and help make it possible to develop that intuition that you probably don't have at first, right? To say this without drawing the picture, like, good luck. Like, I would start by drawing the picture.
Can we have a calculator for these kinds of questions to like graph?
If you weren't given a picture, I would think absolutely.
Okay.
If you were given the picture, like there's nothing inherent about this problem once you have the picture that you really need a calculator for.
Yeah.
It could be a completely non-calculator problem. And even this picture is easy enough to generate by hand to where I wouldn't put past the AP to give you something like this without a calculator, because the functions are so simple. Y equals x and y equals x squared are something that like every AP calculus student can graph on their own without a problem and be able to find the points of intersection and stuff in a timely fashion. Let's continue though, okay? So we need to calculate this area then. So looking at my picture, I hate what they've done here. I'm going to call this R outer, and I'm going to call this R inner. So if I draw my picture, this is like some typical R inner. Everybody agree? So that point is like 0, x, or x, x squared. because this is the curve y equals x squared. Everybody agree? So r inner is x squared. Is that okay? Do I need to make this bigger? We can do that. Now I'm going to do kind of the same thing. I'm going to draw a typical r outer. Nope. So this is like x comma x. Because that function is y equals x. So this is like my r outer. So my r outer is x. Feels okay? Now we're going to integrate. We're going to be slicing perpendicular to the axis of rotation. We rotate around the x-axis. We're going to integrate along the x-axis, so we're slicing perpendicular to it. So my volume then is going to be the integral from 0 to 1 of pi times r outer squared minus pi times r inner squared dx.
Then you just take the strip of that.
Yep, we'll do some integration. So this is, pull the pi out, the antiderivative of x squared. That's easy. And the antiderivative of x to the fourth. That's easy.
How do you see the other pi?
I factored,
Oh,
right? So I just took it both to the front. So I have, yeah, 2/15 or 2 pi over 15. So 5/15 minus 3/15. I'm going to make a denominator, all that jazz. Okay. This method, where we have like a concave figure, what shape does this look like? We call it a washer. You know, like the mechanical hardware, not like a washing machine or a dishwasher, but like the thing that fits around the screw.
That's what a donut is.
It does look like a donut, but the problem with the donut is it's curved on the sides. A washer is like it's a disc with a hole in it. So the typical, this method, we call the washer method, we use if we have a concave figure. So those are two primary methods we're going to be talking about today, disc and washer. Okay? Let's continue on. Okay, what if we take that same situation we had before, where we have y equals x, and y equals x squared, and we're going to rotate this region between them about the line y equals 2.
oh my god.
Take a moment and think about what this shape is going to look like. I'm going to do some doodling on here, and then I'm going to erase in a minute. Is that okay? So I'm going to have like a circle there. And then I'm going to have like a smaller circle there, right? It's going to be flat on the inside, but kind of bulge on the outside. And this is like open in the middle.
So what volume are we taking just in the green?
No,
Everything outside the green?
the red shape that I just drew is like the volume that we're calculating the volume of that thing. Okay, so it's like a funnel. It's open at both ends. There's a hole through the middle, and it's a stupid funnel because it's not like the same width all the way around. It bulges kind of in the middle. What?
What if I had an area in between the two? Like in between the middle and the bottom?
Right, so it's going to be a washer method, right? The cross-sectional area is going to be a washer. Is everybody okay? So I'm going to erase this red thing. Is that okay? Everybody's had an idea of what this thing looks like? You see kind of how I drew it on top of the two-dimensional figure to kind of give myself an idea three-dimensionally what this is looking like? Okay. All right. So what I'm going to draw now is I know that I'm going to have a washer, right? Now I'm going to draw my R outer first. So the center of that figure was the line y equals 2, correct? And the outer function would have been this guy on the bottom, y equals x squared, right? Is everybody visualizing what I'm talking about? This distance is 2. This distance is the y coordinate at that point, right? So this distance must be 2 minus 1. Is everybody okay with that? That's going to be my R outer. And the y coordinate in this case is x squared, because we're on the line y equals x squared. Is that okay with everybody? So A outer is going to be pi times 2 minus x squared squared.
What we say x was?
Huh?
What is x?
Is the variable for our
No, I
function.
know, but like y is equal to x squared, then what's x?
The independent variable for the function.
Okay.
We're integrating with respect to x. That's like the location of the slice. So it's telling us how to calculate the area or the radius for that slice. Peyton.
So the radius is 2 minus the point y.
Well, this is the point x comma y, right?
Yeah.
But we care about the y coordinate because it's a vertical distance back down to the x-axis, right?
Yeah.
Is that
You're just getting rid of that coordinate then in your radius, or like?
okay. Well, broke it again. So this point is x comma y, right? But this distance, this very little tip down here, is just the y coordinates distance, right?
Yeah.
Because this function that xy is on is the function y equals x squared, I can rewrite that y coordinate as x squared. So that's the point x comma x squared. That works.
I know what you're saying now.
Okay.
Thank you.
Yeah, we're just gonna give this a minute. This is really irritating today. I can't. This is the first time OneNote's behaved this badly for me in a long time. Close the program. I don't need you to. No, stop reporting to Microsoft. I want to get the thing back up and running. If I was sitting here doing this on my own, I would have no problem with Microsoft, but I have 20 students waiting for me to continue going on here. And we lost everything that I just wrote. Splendid. Oh, no, this is a different one. There's it. Okay. All right. Now we need a okay. I don't know what's going on. All right. I'm erasing all this stuff now because we need now in our inner, right? That guy would be my R inner. Everybody agree? This distance is 2. If that's the point x comma y, that distance is y. Now, this point is on the line y equals x. So this would be the point x comma x. So y is the same as x, right? So my R inner is going to be 2 minus x.
Are we gonna be able to shortcut that every time? Like, would we be able to just say, like, it's the same as the function every time if it's like a
If it's y equals x?
or like y equals x squared or something?
Yeah. Yeah, that's exactly the relationship that you'll have. All right, so A inner is going to be pi times r squared. Everybody's okay here? Now we're slicing vertically, perpendicular to the axis of rotation because we're rotating around y equals 2. So our volume is going to be the integral starting at 0 and ending at 1 with respect to x, I need more space than that, of pi r outer squared minus pi r inner squared. Is everybody okay here? As this is currently written, I could not integrate this. Would require a u substitution because of the composition, but there's not an extra, in this case, an extra x term floating around. What in the world should I do? Yeah. I'm going to FOIL this out. And likewise, I'm going to FOIL this out. Oops, this is supposed to be to the 4th. That's better. Is everybody okay? I distributed the negative sign when I FOILed it out. That's why all the signs flipped. Is everybody okay? Let's combine some like terms, right? That'll make the integration a little bit simpler, or simpler. So those guys canceled out. And then I have 4x minus 3x squared plus x to the 4th. And now the antiderivatives are fairly easy. So I have, you're welcome. I have a mistake.
So whatever example we did, it's been minus by 0, so it's just in the area of first one. Is it always gonna be like that?
Nope,
Okay.
doesn't have to be, it's just because we started at 0. All right, where did I make my mistake at, guys? Oh, this is a 4. That makes more sense.
Would that be 4x? What do we know with 5x squared? Do you add them?
Oh, thank you. Okay. So I have that then, which will now be a positive value, and I feel much better about having a positive value. Okay. What do we have? Still 10 minutes? All right. I'm not going to worry about crunching the numbers there. Is that okay? Too many fractions too early in the morning. We're going to take the same problem now. Yes? Sure. And this time we're going to rotate about a vertical line, x equals -1. Is okay? So we're like rotating about this line. Again, it's still this same region. All right, take a moment. Visualize what this is going to look like in your head. You know, something like that, right? Basically the same shape, just tilted it or pointing in a different direction, right? Okay. So what I'm going to do now is I'm going to draw in my, obviously since it's got a hole through the middle, it's a washer problem. I'm going to draw my R inner. So that's going to go from my axis of rotation to the inside function. Everybody agree with that? Okay. So from here to here, the distance is 1. And if this is the point x comma y, from here to here, that distance is x. So my R inner is going to be 1 plus x.
Can you just say that that distance is 0.5? That the x is flexible? Or you know?
So for that specific one, yes, but that's a variable. That distance, that radius is changing depending on the slice that we're taking. So I want to write it arbitrarily. You're right, that one looks like it's about 0.5. I'm just drawing like an arbitrary one though, because it helps me visualize like how to write the radius. Is that?
Yeah.
Okay. Now, which way are we slicing here? Horizontally, right? So this expression needs to be in terms of what variable? Y. Well, that's easy. If x is equal to y, this is the same thing as like y comma y. So this is like 1 plus y. So A inner is pi 1 plus y squared. Does everybody feel okay there? I'm going to erase all this so that my thing's not so cluttered. I'm going to write the other one in. Is that okay? So this time we're going to the outer function. So this is like my R outer, right? From there to there is 1. That's like an x comma y, so that distance there is x. So our outer is 1 plus x. Everybody's okay there? What's the problem? This needs to be in terms of y. Now this is the, like, let's just say, we know that this is on the curve y equals x squared, right? So x is the square root of y. And again, there's a plus or minus there. I can discard the minus because this is a length, right? Everybody okay there? So our volume then is the integral from 0 to 1. We'll go integrating along the y-axis. And then we have r outer, or a outer minus a inner. So far, so good. I'm going to FOIL things out. I'll pull the pi's out. So I'm going to have 1 plus 2 square root y plus y minus 1 minus 2y minus y squared dy. Combine some like terms. Those guys go. We have, let's see, we have well, let's write it as y to the 1/2, and then minus y squared. Then we can do our antiderivatives. So this is going to be 2 times 2/3 y to the 3/2. Minus y squared over 2 minus y cubed over 3, 0 to 1. And then it's plug-in time, right? I'm just going to write -0 at that point. So 4/3. If I can do this in my head, minus 1/3 is 1, and then minus 1/2 is 1/2. That was easier. What do you guys think? Lucas?
Can you just explain one more time how you determine your integral a to b, or b to a?
Oh, what the bounds are? Yeah. Okay. So let's go back. I'm going to erase some of this stuff so I can kind of draw this, because it's one of those things, like, I think it's just easier to visualize what's going on here. So when we I'm sorry, that's what I want. 2 to 2. Come on. So it's whatever. It's like this. So I'm slicing this way. It needs to be perpendicular to the axis of rotation, right? This is the way I'm slicing. If I look at my figure, it starts at y equals 0 and ends at y equals 1. So I'm just kind of like eyeballing it.
So it's like the points of intersection?
Yes. Yes, so those points of intersection are giving me, you know, if I'm integrating with respect to x, I'm going from 0 to 1. If I'm doing y, it's also 0 to 1. If this was like 1, 2, it'd be like integrating with respect to y, it goes 0 to 2, right? So just where the two functions are intersecting at. Does that feel okay, Lucas?
Yeah.
All right. I'm going to circle back and look at these other problems because it's a new technique next time since we're almost out of time. 1 through 17 odd, 31 to 33 odd is what I'd like for you guys to work on for next time. I'm going to give you a heads up, I will not be here the Monday we get back from break. I'm going to leave you guys a delta math assignment on this same set of topics that we just did. For that delta math assignment, feel free to use your calculator to compute the integrals. You don't have to do those by hand. The book homework, you should try to do them by hand because based on what I'm seeing as I'm starting to go through the test, you guys could use the practice doing some integrals by hand. Because some of us really struggled there. So we'll talk about the tests when I get back. I don't have enough done to want to talk about them right now, but initial signs were that some of us did wonderfully, but a lot of us kind of had a bed and we said, "Ooh, I might have to go to the bathroom," and then in our bed. Hey,
Wait, so is this homework an optimization due next Sunday or this Sunday?
how about at the end of the week?
Okay.
Does that sound good?
Yeah.
Yes, it should be there. If anything's wrong, come back and find me,
Okay.
and I'd be happy to make sure they get you what you need, but it should be all there.
Okay, thank you.
Also, did I take my quiz during CT? Awesome. Could you email Miss Sager for me? Can you tell me what it is?